Evening, everyone. I kind of jotted down some notes on two-stroke tuning. This is primarily in regards to chainsaws. It's kind of a hobby of mine, and by no means am I the absolute authority on this. I've been doing it for a little while. There's tons of people out there better than me, but this should be good information to get a beginner started and kind of clear some of the muddy waters that are out there. There's a lot of videos on YouTube now, and trying to sort through them all to find someone that knows what they're talking about versus someone that just speaks with authority can be it can be kind of a Herculean task, one of those Gordian knot situations. So anyway, there's my introduction. Probably first thing we need to talk about really is how is power produced, torque versus horsepower, compression, support durations, compromises in two-stroke engine. We're just touching on topics, not trying to go too in-depth here. I don't want to string the video out. It's probably going to be fairly long. Anyway, torque equals force times distance. That's your, I guess, the physics engineering definition of it. You have to modify torque in order to modify horsepower. There is no hold on, let me gather my thoughts again. Torque is one component of the horsepower formula. In order to modify torque, you either modify the force applied to the piston or the distance the piston is traveling, applying pressure to the connecting rod, which is transferring the energy to the crankshaft. That's how you'd modify torque. Modify horsepower, you either modify your torque or modify your RPM. 5252 is just a constant that your torque times your RPM gets divided by to give you a horsepower number. I'm going to say the majority of dyno graphs intersect at 5252 RPM. I don't necessarily know if that's all of them or if that's just the majority of them. Again, I'll let you know if it's something that I don't know, but majority of dynos, they intersect there because that's the constant being used in this formula. So if you want to increase your horsepower, you're increasing your torque or your RPM. Now, back here, we can go back and work backwards. And if we're trying to increase the torque, we can increase the distance the piston's traveling, which that's not happening in one of these engines because there is no power valve. So we can increase the force applied to the piston, and we can increase RPMs in the motor. That's the only two things we're trying to achieve to elicit a gain in horsepower in the motor. Let's talk about a couple things that get kind of confusing. Lots of people like to tune with a compression gauge. Personally, I don't really like that way because you can get the gauge to spit out different numbers. Say if you spray, if you went a little heavy on assembly lube and you check your numbers, Yeah, you check your compression with a gauge right after the motor's assembled. It can be off the charts. I mean, it can be way up there. Also, if you have a 2-ring piston versus a 1-ring piston, I've seen a 40 psi increase, but just because you gained psi on your gauge does not equate to an increase in the force applied to the piston or the RPMs that the motor is turning. These are the two things that we're trying to increase in order to increase the horsepower output. So just because the gauge says it's higher does not mean it is. So my note here says, your PSI in your gauge only minimally matters. The gauge is better suited for verifying changes in engine health, and engine health. It does not tell you anything about compression ratio. Compression gauge does not equal compression ratio, and the PSI is only telling you part of the story. The next one. Torque is a characteristic. This one kind of bugs me. A lot of people, I've seen a lot of comments say, "Hey, can you tune that saw for torque? Can you tune that motor for torque? Can you tune it for torque?" If you're using torque as an operating characteristic, majority of the time when someone says, "Oh man, it has a ton of torque down low," most of the time it's just slow. A big displacement motor without a whole lot of RPM, without a whole lot of cylinder pressure, it's just slow. Your chains are typically tuned to cut around 10,000 RPM. If the motor can't handle that load, it won't rev out properly, and it may not necessarily die out, but with it being loaded down so hard, it's not torque. It's typically just slow. And here we go. I'm gonna hammer on this one pretty hard. If you go back to torque, you're trying to tune for torque, you can increase your force applied to your piston, and that's the only thing you can try and increase there. You can increase your the length of your exhaust stroke, your power stroke, by lowering your exhaust, but that's not something that you can change once you've done it. Once you've done it, you're there. And if you changed all of your numbers back around just to tune for this one, you could be leaving a whole lot on the table just to build something that's slow and luggy. Can you do it? Yeah, probably. Is it wise? No, it's just going to build a motor that's probably hot and not going to hold up very well, or not going to give very good performance. And the other one, I know I put fallacy down here. That's just means something is pretty much false and kind of based on either a misguided or not logically backed belief. These three things fall in here. Blowdown. A ton of builders, tuners talk about blowdown. Blowdown is the number in degrees from your exhaust to your transfers. This is when your exhaust opens, this is where your transfers. Numbers are typically laid out like this. So this would be intake, transfer, exhaust. If you're telling me blowdown is what matters, Oh man, it's got to have 20 degrees blowdown. It's got to have 20 degrees. It's got to have 20 degrees. 75, 120, 100. That's 20 degrees blowdown. 75, 125, 105. That's 20 degrees blowdown. 75, 130, 110. You guessed it, 20 degrees blowdown. If blowdown is the driving force here, then these should all run the same because they should all have the same blowdown. If you're just using it, saying, hey, I have this exhaust with this blowdown, that's changing that's just as a mental marker to mark your intake timing, that's fine. But saying something has to have a specific blowdown number, totally irrelevant. And I think that that's just the first term a lot of people learn and understand what it is, not necessarily what it does, and they like to throw it around because it makes you feel like you know something. So here's things to kind of watch out for. These are the two that you're going to run across on YouTube a lot. And again, not picking on you. There's times where I thought both of these things mattered a whole lot, and I'm just here to tell you they don't. Just save you time and get you on track a little quicker than normal. So we've covered how power is produced. So here's what's going on in the engine. Your air flows through your carb through a Venturi effect. Carb is going to add atomized fuel to the air. The air-fuel mix is drawn into the crankcase, where it's pressurized by the downward stroke of the piston. After the piston closes the intake port, your pressurized air-fuel mixture is forced through the transfer ports into the combustion chamber. This process scavenges some of your exhaust out as well. Then the mixture is compressed and ignited. Pressure from the combustion applies force to the top of the piston, forcing it down at a rapid speed. Force applied to the piston is transmitted to the crank via the connecting rod. This is where your torque is made, because torque is just force times distance. Distance is going to be the distance from top dead center to when your exhaust port opens. This number is remaining fixed in our situation. So this is kind of crossed out. So we're left with just the force from combustion that we're trying to alter. Now, as the crank rotates over time, you'll get horsepower. What's the M and RPM stand for? Minutes. You have rotations per minute. So rotations is your distance. Actually, no. The torque already has your distance factored in. Torque has your force factored in. RPMs is your time. How many times can you give that torque output, in a given minute? So now we're left, we can increase force and RPM. And that's where I talked about it here. You can increase your combustion pressure. We'll talk about a few ways to do that. You can increase RPM. Talk about a few ways to do that. And if you got to increase your distance, which in certain instances is a very valid thing to do, you lower your exhaust roof. Hopefully that's clear on how power is produced. Now, how do you decide where to go? Let's go over here. I made kind of a flow chart. It's probably not all encompassing, but this is just a good general set of basics to look to if you're trying to increase performance in a chainsaw. Is it in proper operating condition? Yes or no? No. Address functional issues? Yes. It's operating correctly. Are there external components restricting performance? That would be your intake or exhaust. That's what I'm specifically talking about there. If the answer is yes, we'll alleviate exhaust or intake restrictions. If the answer is no, you have no restrictions, you can proceed to here. Is there room for cylinder modification? Sometimes there is, sometimes there is not. If there's not room for cylinder modification, your intake and exhaust is really all you have to mess with, and you're done. If you got room for cylinder modification, you need to find your cylinder restrictions. Is it lower on compression? Do you have bad port timing? Do you have bad ignition timing? What? Personally, I like to start with compression ratio. I'm aiming for 7.5 to 8.5 to 1. It just depends on how much is there and whether or not I can hit an adequate exhaust duration for my purposes. And that's with a 20 to 30 thousandth squish. If you got your compression right with adequate exhaust, your transfers between 125 and 120 after top dead center. If they're 130, probably worth taking them up to 125, seeing how it runs. If they're 125 and it's still, your power band's a little bit low, maybe pushing them closer to the 120 mark would be a wise decision. So if you answered no, the transfers aren't there, you adjust them, make sure your roof for the transfers is flat. I'm pretty sold on flat roofs for the transfers. Is there a situation where flat roof might not be might not be the most optimal thing? I'm probably, there's too many motors to name. I haven't been inside all of them, and I haven't been to the point where I can sit there and definitively say they all have to be flat. Personal experience and experience of people more experienced than me indicate flat is the way to go in the vast majority of cases. And is your feed angle directed properly? If you have all of your transfers, pretty rough circle, but say you got transfers here, this is going to be your intake side, you got transfers there and transfers back here. These are the primaries, these are the secondaries. Ideally, you'd like everything directed toward the intake. If you have one that's shooting out flat and another's kind of kicked off to the side like this, whenever you hit an exhaust stroke, this charge is being sucked out of the exhaust and you're going to be left with impure mixture in the chamber. That's not going to aid in production of power. You want as much air-fuel mixture from your transfers in the cylinder by the time the exhaust closes as you possibly can. If your transfer angles are not set up properly, that's just going to hurt you. Now, it's got all on subject, but not all in order. So if your compression and your ports are adequate, then increasing ignition advance or advanced combustion chamber work are your only methods for increasing power output. If you increase your advance, you're igniting your air fuel charge earlier, you're building pressure earlier, and that can put your peak cylinder pressure at a more advantageous point in your crankshaft rotation. If it's less, then you're building pressure too late. If it's too much, you're building pressure too early and having to fight through the stroke, and it's just not balanced. Everything in these motors is a compromise. If it helps you in one direction, it's fighting you in the other. You're just trying to get everything working as best as you can. And then advanced chamber work, you're going to have a couple different combustion chamber designs. Say here's the cylinder. Some of them have a squish band and a hemispherical chamber. Some of them have really no squish band and a hemispherical chamber. No squish band is supposed to be more advantageous in high RPM situations, because if you look at it, your spark plug's usually here, it ignites, and you have straight line path for flame propagation throughout that whole chamber. If you have a squish band, you're hitting this point of the chamber first, and then once the piston gets moving, you've trapped a little bit of charge here, and then all that goes off. This gets really in depth. It's a whole nother rabbit hole. And then if you change one of these too much, then you may have to change your ignition timing again. Then, so we covered my flow chart. Like I said, personally, I'm starting with compression, and this is why I made a note. Numbers in the graph are for illustrative purposes, so they aren't exact, but they illustrate my point pretty well. For each point increase in compression, your cylinder pressure, which is our force and our torque measurement, that's the force that we're talking about in torque. Your cylinder pressure during combustion increases. That's going to be an increase in power. If all your other factors remain the same, that is a guaranteed increase in power. And that is going to happen until other factors push in the opposite direction. Other factors being detonation, slowing the piston more than what the flywheel can compensate for. Personally, have not had that. Can it happen? Maybe, maybe not. Inability to ignite charge, inability to get the motor started. Compression is a good thing. Too much compression is not. And here's your note with the cylinder head and combustion chamber design. It has massive influences on optimal compression ratio, and it has a ton of influence on pretty much everything you adjust in these motors. But here is a chart kind of showing effects of compression. X being corrected compression ratio, that's down here. The Y is going to be your percent power gain with your compression increase. So if we start 6-to-1 compression and jump to 7-to-1, that's like a 10% increase. Again, these are just made up numbers, but the chart follows pretty well. Going from 7 to 8, you're still gaining. 8 to 9, you're still gaining. And personally, I think 9 is probably about max for 2 strokes, but again, this is just to illustrate a point. Say you max out at 10. 7 got 10%, 8 got 5% more, 9 got 3.5% more, 10 maxes out. Well, you push past that, now it's going to start dropping again. There's just other things that come with an increase in compression that can go, if you go too high, it's going to rob power. You can create more heat. You can create a situation where the flywheel is just barely storing enough energy to keep it going at idle or whatever. But there is a sweet spot. I think it's probably somewhere in that 7 to 9 range. I think the sweet spot's more in that 8 to 9 range. But you don't always get that much to work with. Once you've addressed your compression issues, you can switch to ports, duration, shapes, and angles. Once compression reaches the point of diminishing returns, your other methods left for improving your power output is port arrangement and cylinder. We touched on that in the flow chart. Port timing, the angle at which it feeds into the cylinder, and the area of the port has a significant effect on RPM range that you're trying to make power. Typically, more duration is going to raise the power band. That's just how it works. Exhaust duration has a significant effect on power production. It is typically where you have to make the most compromise. Raising the exhaust can reduce your mid to low RPM power, but has the potential to raise peak RPM and increase power higher in the rev range. That's typically where you're going to have the difference between like a race saw and a work saw is your exhaust roof probably going to vary by a couple of degrees, in the realm of probably 3 to 7, somewhere in there. It's going to be it'll probably have, your work saw will have a less exhaust duration and a lower roof at 99% of the time. Providing your intake has adequate area and duration, it'll usually yield the least effect on peak power. Too much intake can make a motor less responsive on the throttle or boggy on the low end, and too little can limit your power production and RPM capability. So I hope that cleared some of it up for y'all. If you have any questions, if you disagree with things that I've said in here, go ahead, throw it in the comments. If you can give me an evidence-based reason for why something I said is wrong, go ahead and do it. I'm here to learn, and I'm admitting that I don't know everything, but I'm trying to help people that know less than me. You run into a situation in the world called standing on the shoulders of giants, where each generation after you should make more progress in whatever they're trying to make progress in, because there's generations before them that have done work and found answers. So you should be able to study all the things that someone before you has done, so you can make progress. You can progress to their level pretty rapidly, and it gives you more time in life to progress past that. So that's my my intro to two-stroke chainsaw tuning. If you got other questions, concerns, comments, some FUs, whatever, just throw it in the comments. Thank y'all.